Let's examine another category of integrands in which it is appropriate to apply the integration by parts method. In this category, the integrand will be the product of a polynomial function and either a logarithm or an inverse trig function. Now, in order to understand the vocabulary that I'll be using, first note that algebraic functions are composed of operations familiar to real numbers, such as addition, subtraction, multiplication, division, roots, and powers. Now, functions which are not algebraic are said to be transcendental. These functions include trigonometric functions, inverse trigonometric functions, exponential functions, and logarithms. So for the case in which the integrand is a polynomial function times either a logarithm or an inverse trig function, we're going to choose u to be the transcendental part of the integrand. So let's give this a try on example 3. We're going to evaluate the definite integrals exactly. But first, let me apologize. I have given you an integral that is undefined because of that 0 lower limit. So let's change the limits of integration. Lower limit will be 1, upper limit will be e. So let's consider the integral from 1 to e of t to the 6th times natural log of t dt. Notice that an ordinary u substitution would not work for this particular problem, but we do have the product of a power function and a transcendental function. So in the case of a power or a polynomial function times a transcendental function, we're going to let u equal the transcendental part, which in this case is natural log of t. Differentiating both sides, we obtain du equals 1 over t dt. Now remember, with integration by parts, we choose two substitutions. We have u equals natural log of t, so what's left in our integrand is t to the 6th dt. We're going to let dv be all those leftovers, t to the 6th dt. Now, as I'm working my way up the page, generally you're increasing the degree of your function. So we are integrating as we work up, differentiating as we work down. So the integral of dv, that's going to give us our function v. The integral of t to the 6th is 1/7 t to the 7th. And remember, we don't need an arbitrary constant of integration with the IBP process. Now we're ready to apply the formula. The integral from 1 to e of t to the 6th times natural log of t dt, according to integration by parts, is u, that's the function natural log of t, times v, 1/7 t to the 7th. Now, this is a definite integral, so I'm going to go ahead and put a pause here. We're going to evaluate that from 1 to e. So we have u times v minus the integral of voodoo, or v du. That's 1/7 t to the 7th times du, which is 1 over t dt. So again, to be clear, we are applying the integration by parts formula. We have u times v minus the integral of v du. So that is our guiding formula to get everything in the right place. Next, let's simplify our integral. And by the way, let's rewrite this a little simpler as well. I'm going to write this as 1/7 t to the 7th natural log of t, and I'm going to postpone its evaluation until I'm finished with this second integral over here. I'm going to factor out the 1/7 as a numerical coefficient, and then we have t to the 7th times 1 over t, which reduces to t to the 6th dt. We can go ahead and evaluate that second integral to get 1/7 times t to the 7th over 7. Then I'm going to evaluate the entire expression from 1 to e. Now, before we move on, I want to point out why this particular method works. If you notice this integral over here, recall that we chose dv to be this t to the 6th function, and we have u to be natural log of t. Since u was the transcendental part, and transcendental functions have algebraic derivatives, the v and the du nicely combine over here in this integral. Since they're both algebraic, they simplify, which yields a very simple to evaluate antiderivative. So that's kind of the motivation for why we let u be the transcendental part. Now let's go ahead and finish evaluating this definite integral. So the first thing that I want to do is plug in my upper limit e. So we're going to get 1/7 e to the 7th natural log of e minus, and let's go ahead and call that 1/49 e to the 7th power. So I'm just combining those constants there. So there's our upper limit. Now we're going to plug in our lower limit 1 into our antiderivative. We're going to have 1/7 times 1 to the 7th natural log of 1 minus, again, let's call it 1/49 times 1 to the 7th power. Now we can simplify this very nicely. Recall that the natural log of e is equal to 1, and the natural log of 1 is equal to 0. So this entire term is going to zero out. This will then simplify down to, and I'm going to write it as concisely as possible. How about we call it e to the 7th over 7 minus e to the 7th over 49. And remembering to distribute this negative, we have plus 1/49. If we go ahead and get a common denominator of 49, we would have 7e to the 7th minus e to the 7th plus 1, or how about a final answer of 6 e to the 7th plus 1 divided by 49. Now remember, that is the exact answer. If we wanted to approximate it with the calculator, we could certainly do so, but our default mode will always be exact unless an approximation is requested. So looking over this problem to understand the big picture, we are applying the integration by parts process, choosing u to be the transcendental part because its derivative is algebraic and combines nicely with the algebraic v. Let's use this same strategy on example B. Now, it doesn't look like there's much to example B to begin with. We're looking at the integral from 0 to 1 of arctangent of x dx. Now, keep in mind at this point, you have learned how to find the derivative of arctangent of x, but we have not yet explored any formula for integrating arctangent of x. So the way we're going to handle this definite integral is really quite clever in my opinion. We're going to execute this antiderivative using integration by parts. The only choice we have here for u is to let u be the transcendental part, or the only part we have there, arctangent of x. Now the reason that we choose that is because its derivative is algebraic. Now remember, we have learned the derivative of arctangent of x. In this case, it's 1 plus 1 over x squared dx. Now we are in the integration by parts process, which means we choose two substitutions. We have our u, and we have to choose a substitution for dv. Well, at this point, we have u representing arctangent of x. The only thing left in the integral is dx. So we will choose dv to be dx. Now let's integrate. The integral of dv is v, and the integral of dx is x. Now watch how this one pans out. We have the integral from 0 to 1 of arctangent of x dx, and applying our integration by parts formula, we have u times v. Now I'm going to put it v times u just to make it readable. V is x, u is arctangent of x. So we have u times v minus the, oh, and by the way, this is a definite integral, so I'm going to put a pause right here to remind myself that needs to be evaluated from 0 to 1. Minus the integral from 0 to 1 of v, which is x, times du, which is 1 over 1 plus x squared dx. So what we're doing here is taking advantage of the fact that the derivative of arctangent is algebraic, which means it's going to combine nicely with our choice of v, making this an easily executable antiderivative. So I'm going to take one step to rewrite that second integral. Maybe that'll trigger your imagination for how we are to handle this one. We have the integral from 0 to 1 of x over 1 plus x squared dx. Now remember, integration is primarily a problem of recognition of patterns, that is. So to figure out how we're going to integrate this second integral, we need to look at the pattern of the integrand. Notice x over 1 plus x squared is a rational function. It doesn't match any of our integral formulas for the inverse trig functions, but notice it is a proper rational function. One way that we can handle the antiderivative of a proper rational function is to let u equal the denominator. And we've already used u, so I'm going to call this u sub 1. This is a different substitution. So let u be the denominator, then the derivative is 2x dx. So again, I'm going to hold off on evaluating this part and just copy it down. And then we can rewrite our integral in terms of u. We do have to be careful here because the limits 0 and 1 are x values, and we are changing from the variable x to the variable u. So I'm going to put stars there to prevent me from accidentally plugging those in for x. So notice we have 1 over 1 plus x squared, that's 1 over our variable u sub 1, and then the leftovers would be x dx. We have that here as long as we isolate it in this derivative equation. So we have 1/2 du sub 1 for dx. Again, I'm going to carry this down. I like to do one thing at a time. So I'm going to carry this along. And then our antiderivative is going to be minus 1/2 natural log of the absolute value of u sub 1. This is also a definite integral, but I cannot use 0 and 1. And I am not going to update the limits from x values to u values. I'm going to go back and recover my original variable. So my original variable was x. So continuing our work here, we have x, arctangent of x. I'm going to rewrite this as minus 1/2 times the natural log of the absolute value of 1 plus x squared. So I'm just replacing u with its equivalent in terms of x. Now that everything's in terms of x, I can evaluate the entire expression from 0 to 1. Everything is in terms of the single variable x. Our original limits of integration 0 and 1 were x values. So now we're ready to proceed to the next step. So I'm going to begin by plugging 1 in for x. We're going to have 1 times arc tangent of 1 minus 1/2 times the natural log of 1 plus 1 squared is going to give me 2. So there is our upper limit plugged in. We're going to subtract the antiderivative evaluated at the lower limit of integration. Now, when I plug 0 in for x, we're going to have 0 times arctangent of 0. That's easily going to give me 0. And then we have minus 1/2 times the natural log of 1 plus 0 squared, which leaves us with natural log of 1. Let's see what we can evaluate. Arctangent of 1. Now, remember, when you evaluate an inverse trig function or an arctangent function, we're looking for an arc or an angle. So I'm going to find the angle on the unit circle with a tangent ratio of 1. We would obtain exactly pi over 4. Be absolutely sure that you evaluate in radians, not degrees. Now, there's not much I can do with this term. We'll leave it 1/2 natural log of 2. And then notice down here on the end we have natural log of 1, which is 0. So it looks like our entire lower limit zeroes out. And the exact value of our definite integral then would be pi over 4 minus 1/2 natural log of 2. So we applied integration by parts to this seemingly simple integral problem, integral of arctangent of x, and we were able to execute the definite integral. So remember, you're watching for patterns in the integrands. If you have the category, polynomial function, here it is, polynomial function times either a logarithmic or an inverse trig function, then you're always going to let u be the transcendental part. That's the key of working this category of problems.